Welcome to my poster titled Numerical Modeling to Assess the Changing Coastal Risks from Nor'easters with Sea Level Rise in New England. Coastal regions in New England are at risk of coastal flooding from storms such as nor'easters. Examples of this are shown in the photo on the upper right, which shows coastal flooding from surge in a commercial area in downtown Provincetown, and wave-induced flooding in the animation is shown for the same storm event in another area along the Massachusetts coastline. Sea level rise will change these risks, and this poses two challenges to DHS. One, understanding the changing vulnerabilities at their own coastal facilities, and two, understanding the changing vulnerabilities in the region such that FEMA can continue to prepare and respond to coastal flooding emergencies. The research I'm involved in to address these challenges includes performing numerical modeling studies using the coupled ADCIRC-SWAN model system to simulate the effect of sea level rise on the coastal impacts from nor'easters. And this poster details the modeling study focused on the northeast of Cape Cod, shown in the middle figure on this slide. The first step was to tailor the mesh for the model application. We started with a regional mesh of the Atlantic Basin, and it was extended over land to an increase in resolution in order to be able to capture the coastal processes and inland and overland flooding. We also assigned high resolution elevations from a USGS post-Sandy LIDAR developed data set. The mesh resolution varied from approximately 26 kilometers down to 20 meters in the coastal regions. We selected the January 2nd through 6th, 2018 nor'easter because it was an event that was known to observe to have high water levels. It's based on the Nantucket Island NOAA gauge station, which showed 3 feet of storm surge during this nor'easter, and also due to coastal flooding reports, which detailed extensive coastal flooding. We generated the meteorological forcing using the output from the ERA interim data set, which is animating in the bottom of this slide. This is a reanalysis data set of a global atmospheric model forecast. We incorporated sea level rise for the sea level rise scenario using the ADCIRC NOAA attribute file, where we assigned 1 meter of offset the mean sea level by 1 meter for all the nodes in the domain. And then we ran the model and of the 2 simulations and compared the results. The model predicts the time and space varying water surface elevation, currents, and wave heights. We developed the maps of maximum inundation using the maximum water level from the simulation and subtracting the bottom elevation. This is shown for the simulation without sea level rise on the top and with sea level rise on the bottom. And the colors reflect the depths. So comparing these two, you can see that the footprint grows and deepens in a lot of areas and appears in some areas where it wasn't present without sea level rise. In the areas it does appear, it also crosses the entire width of the peninsula. We also looked at the change in the maximum water level during the storm, and we mapped the differential at some select coastal sites, which is shown in the figure on the left. What was interesting about this was that on the Atlantic side, the differential was slightly lower than 1 meter, and on the Provincetown Harbor side, the differential was slightly greater than 1 meter, and thus not matching the assigned interval of 1 meter. We also performed a time series analysis looking at the total water column height and the significant wave height. The total water column height was shown to be similar in the 2 locations. The plot on the left is from the Atlantic side, and the plot on the right is from Provincetown Harbor. The increment stays the same approximately through the simulation. The blue is the no sea level rise scenario, and the orange is the with sea level rise scenario. The significant wave height varies significantly from the Atlantic side to the Provincetown Harbor side, where there are much greater wave-induced wave heights on the Atlantic side, and there's a much greater change in the wave heights with sea level rise, whereas in Provincetown Harbor, it's a negligible change. This study and analysis found that the sea level rise increases the total water level, which increases the inundation footprint during tides and storm surges. The increment of the increase of the peak water levels does not exactly match the assigned increment, which was assigned to all the nodes to reflect the sea level rise. The peak water levels vary by about plus or minus 5% depending on location, where the Atlantic side had slightly less than 1 meter and the Provincetown Harbor side had slightly greater than 1 meter differential. The inundation during the storm cross the entire peninsula, which would leave a large portion of Provincetown without the ability to evacuate without crossing a flooded waterway. The storm-induced significant wave heights were much greater on the Atlantic side than they were in Provincetown Harbor, particularly at the peak of the storm. And also the change in the wave heights were much greater on the Atlantic side than they were on the Provincetown Harbor site, with approximately 1 foot increase in significant wave height at the peak of the storm. Thank you for listening.